Welcome to another video presented to you by Bob D. Hilster, your particle model guru. Well, this video is the beginning of a series of videos I'm doing on my book, a book titled Gravity is Not Free. This is going to be an introduction, an overview of the book, and I will go into more details in subsequent videos to give some information about that. Gravity is Not Free is the title of a book written by myself. It spans a period from early 1990s to the spring of 2015. And here's a review copy of the book. Was handed out at the a conference a couple of years ago, and it has been edited and been marked up and corrected, and hopefully will be issued with a different cover. There are 4 parts to the book. The first part is about Dave and how he got involved with science, and then, of course, how he got me involved in science. Part 3 is titled A New Equation for Gravity. It goes into a straightforward technical presentation where these are personal stories. This is strictly about the equation and about the work I did in gravity. And part 4 is a group of white papers explaining some stuff in a little more detail that is not covered in the natural flow of the part 3. From the foreword of the book, it states, gravity is not free because motion is not free. You can't move something and not expend energy, calories, gasoline, or rocket fuel. And even energy and calories, which are kind of not really things, there's some sort of fuel source behind that. And yet gravity is there every hour, day, week, year, and beyond, causing the motion of the planets and the apple to fall off the tree. If gravity is free, then we have perpetual motion without expending any form of fuel or energy. So how can gravity be free when all other forms of motion uses up some form of energy? Well, the reason is because it gets partially used and then replaced. The Lesage theory of gravity, which is the gravity work that I've done is based on, assumes that there are gravity particles coming from all the stars. Now, he never said that. That's my statement. That's what I perceived, understood to be true as I worked on gravity. The only place these particles could logically come from was from the stars in the universe. And there is a set of these particles homed in on each part of an object, not just the center of gravity, but on each part. Most pass through while a few hit and scatter. You'll recognize some of the terminology I use quite often. Those that hit push the object. Pushing theory of gravity. They scatter and move out in random directions after they hit. And they are lost to that set. That set that's homing in, they're lost before they get to the point where they're supposed to be. They're lost. And that in that sense, they get used up because they are gone. They are no longer part of the set. But in the next interval of time, the distant stars replace them with a new set. Keep in mind, these particles move at speed c, and the object, the apple or the earth, they're moving very slow, and so it doesn't take much time. In some very small interval of time, it's a new set. This makes gravity look like perpetual motion. As long as we have these stars out there generating these particles, and as long as we understand that that is the form of gravity proposed here, it certainly would look like perpetual motion, but it's because of these many, many, many stars out there. So part one is about Dave. This is going to be in a little overview. Dave met Dr. Riccardo Carasani in the early 1990s, and he helped Carasani with his book, Storm in Physics. While helping Carasani, David understood that special relativity could be wrong. That's what Carasani was saying, and that the neutrino was invented to save special relativity. All you got to do is ask Dave about the neutrino, and you'll hear about it. Carasani was also convinced that gravity was a pushing force, not a pulling force, and that it was based on Lesage's theory. So in the process, David decided to make a film documenting the problems and do a gravity experiment. Well, the film is titled Einstein Wrong, the Miracle Year, and you can get go to this link and this screen will pop up. And it says down here, I know it's hard to read, you can rent it for $3 or buy it for $10. And yes, that's a picture of me. I'm bald because I, at this point, was finished chemotherapy, and I'm holding my granddaughter a few hours after she was born. Her name is Lawanda Leah, and my wife Patricia is kissing her on the forehead. And this is the film that he made, and it contains this experiment. So part two is about me. Dave came to my condo in Long Beach, California, and asked me to help with an experiment. I said, "What experiment?" I didn't know about it at the time. Dave gave me this DVD that gave the background for an experiment and how it was to be performed. And this is the experiment. It's a takeoff of an experiment that John Mitchell had done originally, and Henry Cavendish did when he determined the value of G for Newton's equation. Well, when Cavendish did his experiment, these two blocks and these two blocks weren't there. Just one block here and a ball here at the end of this bar, and a block there, and it's hung by a tension wire. And he did his experiment. I'm not here going into details of experiment, but when these blocks are not here, clearly Cavendish was expecting the ball to move this way, and he compared the torsion force of the wire equated it to the gravitational force caused by gravity between these two objects and these two objects, and got the result. What Dr. Carasani suggested was to show that it's a pushing force. He suggested to add these two and these two, and with a gap in the middle. Now, when you think of Newton's and the standard theory of gravity, this is the larger mass. You would expect this object to go this way, and this one to go this way. There's two of them balanced on a wire so that vertical gravity is canceled out. That's what you expected to do. What Carasani was saying, no, the gravitons, the gravity particles coming through here, would push the ball this way because they're being blocked coming through here, and therefore he said the result is it ought to go back this way. Even though the standard theory says it should go to the large mass, he's saying it'll go to the small mass. And so when you do the experiment, you're expecting the barbell to go that way. Well, the first thing I did in terms of helping Dave do this experiment, I said, how am I going to compare the two and know what's really going to happen unless I have an equation for the pulling force? So I assumed this was an equation for the pulling force. You argue the point, but that's the equation I used to compare it to this equation. I spent my first time, the first thing I did was to develop this equation. I'm not going to go into details here, only to say that these two equations they don't even look alike. Number one, G is not in here. 2r squared is not here. So I developed these two equations and I did a calculation. I based it on the experiment, on all of those bricks of lead and those two balls hanging on a wire. I calculated the force on the ball as in different positions within the open space. And I did a two-dimensional calculation of the force. This is the result I got. When I saw this, I realized Dr. Karazani was wrong. According to these, if my equation's right, and Newton's equation clearly has been validated, this shows them the force on this is not exactly the same. They're different equations, but they're not going to go in opposite directions. I decided that I might get a better answer if I did a three-dimensional. And I had to do a three-dimensional calculation, not just two-dimensional in the XY plane, but three-dimensional, accounting for all the mass of the ball, all of the mass of the lead bricks that surround the experiment. And I got this one. Look how close it comes here. Look how close it comes there. And actually, if you, I didn't explain that before, but the direction of the force here is one direction, the direction of the force here is the other. Force is positive, force is negative. So the force isn't always one way. It happens in both directions, primarily this way and then this way. So I moved on. We did the experiment, and if you read the book, you'll find it failed. We didn't have enough lead. You can go into a lot of it, but it failed. But we went to a conference. I presented the paper that Dave, and I told Dave that I was done. I didn't know at the point in time. I said, well, I did the experiment. That's fine. I had no idea at that point, at the end of the conference, what I would do. But I did continue. Interestingly enough, it was a few years later when Dave was working on the film. He was now doing it. He had all the film he needed, including film at that conference, film of me presenting the paper, film of us doing the experiment. And his technical editor asked Dave, why did your dad continue? And it's an interesting question because I did. And David didn't know. He comes in and he asks me. This was my answer. The force curves were supposed to give opposite results. The matching force curves suggested, they didn't match perfectly, but they matched close enough that Karazani's prediction was really wrong. And I wanted to know what made my equation, an equation that did not use G or R squared, could give a similar result. So I continued. The paper was given in 2007, and I actually started soon after that working. It took me all of 2007 to come up with one idea about how my equation could work, just like Newton's. Well, I worked on a lot of different things. Part 2 covers a lot of different things, anomalies and the experiment, and then finally a calculation. I wanted to find the values of f sub p and I sub f. These are two constants. They're not, I don't really call them, I call them virtual constants. They're not absolute constants because they are dependent on other things. Newton has one constant of proportionality for his equation. I have two, and they're called f sub p and I sub f. I sub f is the interaction factor. I've talked about the interaction factor over and over and over again, whether it's gravity, light, magnetism, circuits, chemistry, biology. Talk about the interaction factor when particles interact with each other. The interaction factor is a proportion of how many interact as they pass through an object. It helps you estimate, if you can find this, it's telling you what percent will interact for a given object. F sub p is something I haven't talked about much. I'm going to give you its name. It's the potential force of gravity at any point in space. The problem is when you look at galaxies, the potential force of gravity at any point in space is not the same. It's dependent on the mass distribution around it. And so I was trying to calculate these two. And while still working in California, now it's already mid-2014, I used my equation to calculate the value of this. The data came from an experiment done by Quirino Majorana in 1920s. You can find this in a book titled Pushing Gravity. And I used that data, and I finally got the values, although they're not confirmed. And I got the values in 2015 because actually in July of 2014, Dave, his wife and family, Doris and Lawanda, my wife and I all moved to Boca Raton, Florida. But when I got here, I continued the calculation, and I finally got an answer for these values in 2015, and they're in the book. But they're preliminary. They're not confirmed. I'm very uneasy about stating the value, but they're in the book anyway. And then part two, towards the end of part two, including when I was in California and in Florida, for about 2 years, Paul Schroeder and Artie Rantham, two people who agreed to work with me on a paper to describe how an electromagnetic wave could cause gravity. It's kind of totally a different approach, but we did it, and there is a paper in the CNPS 2015 proceedings written by Paul, Artie, and myself. Oh, wait, we did that, and we finished that, but after that, I started to ask this question. This was a really key question. And I decided that in opposition to this, I would now, instead of using an electromagnetic wave, which is like light, I would now use a particle and ask the question, how could I make a particle act as light, as an electromagnetic wave? It's just the opposite around. Part two ends there with the hint that it ends with the conference in 2015, which was here in Boca, and it gives hint about the work of the particle model. And but it's not the particle model information. It is not all the work that was done since 2015 is not there. That will be in the book Dave and I are writing on the particle model called Hacking the Universe. Part three of the book is a straightforward technical presentation of the gravitational equation and all the things that I evaluated and looked at, anomalies, experiments. There is no personal story there, although it does proceed somewhat chronologically because each chapter ends at the conference. Each chapter is essentially 1 year, and it tells what I did during that year, working primarily on gravity. Part four is a compilation of 5, I call them white papers, that gives more background information and clarification of certain issues that help explain some of the work in part three. The 4 papers are force and mass. I've talked about this many times. R squared, is it really a law? Virtual constants. My opinion is that even the universal gravitational constant is not an absolute constant. It's a virtual one. And clearly in my equation, those 2 constants cannot be considered absolute. They have a value at a given region, at a given time. And so that's what that paper is about. Then there are the three main objections. In the book Pushing Gravity, edited by Matthew Edwards, published in 2002, there's main objections that really killed Lesage's theory and why you read today that it's totally discredited. I address those objections. Then I talk about the math that you use for the particle model versus math that is used by others. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time. The next time this case, I will explain more detail of part 1 of my book, Gravity is Not Free. Thank you for your attention.